Hi, how are you doing? I'm Lonnie Palama, and previously we talked about a special right triangle, which was the 45-45-90 triangle. Today I'm going to continue with the same thought of talking about another right triangle, which includes the 30, 60, 90 degree right triangle. Okay, so let's go ahead and start on this. I've got here an equilateral triangle here to my left, and I'm going to specify that triangle with the vertices of A, B, and then C. Note also that I've got a line here that in fact bisects one of the angles, angle B here. It bisects it. And I'm going to call the midpoint between A and C as point D. In addition, I'm going to specify some values for each one of these. In terms of the angle that is opposite of the 30 degree as opposed to the 60 degree or to the 90 degree, the leg opposite of that I'm going to identify as X. The hypotenuse, which is segment AB, I'm going to identify as 2X. And the altitude that was drawn, or the long leg, I'm going to specify that with a symbol of A. So what we want to do is essentially, let's do a derivation that in fact will help us to understand what is the relationship between the short leg X, the long leg A, and the hypotenuse, in this case 2X. So let's go ahead and proceed forward. Remember on the Pythagorean theory, which we spoke of before, states that the squares added together equals the square of the hypotenuse, which is a squared plus b squared, in fact, equals c squared. Well, let's use the values in terms of a hypotenuse, short leg X, and A for our long leg. Let's convert that via this Pythagorean theory. So in fact, the short leg I'm going to identify first as x squared plus a squared long leg, in fact, equals our hypotenuse, or 2x raised to the second power. Let's go ahead and continue on this. So therefore we have x squared plus a squared equals 4x squared. Let me scroll this down, or scroll up, excuse me, so we can continue. Let's go ahead and combine terms is the first thing. So we're going to combine the x squared with the 4x squared and subtract it from that. So therefore we have a squared equals 3x squared. Now to get rid of that exponent, let's go ahead and take the square root of both sides, positive square root. And so hence we will end up with, just a little too much there, taking the square root, I'll just specify here, taking the square root of both sides. Square root of a squared, in fact, gives us a. Square root of 3x squared will give us x times the square root of 3. Now note that this value, a, equals the long leg, which in fact was identified as a. Let's combine the three of them. Let's see if there's any relationship. Originally, in the problem, the hypotenuse, let me abbreviate that with HYP. HYP will be the hypotenuse, and the value that was given to us was 2x. I'm going to take the short side, which in fact, I'm going to abbreviate with an SL for short leg, and that value that was given was x. And then I'm going to give you the calculative value of which we calculated for the long leg, or abbreviated LL, long leg, and that was equal to x square root of 3. Well, let's take a look at all three of those. What we see here is that we can come up with a relationship of one, hypotenuse versus the short leg versus the long leg, and these are the relationships that we see. We know that 2x, hypotenuse, is 2 times x, the short leg. So the hypotenuse, again, the relationship is, if we in fact have a value of the short leg, we therefore can solve for the hypotenuse by multiplying it twice. Let's see if there's another relationship that we've uncovered here. If we take the short leg versus the long leg being opposite of the 60 degree, short leg being opposite of the 30 degree, we will note that it is the long leg equal to the value of the short leg x times the square root of 3. And in these triangles, these three particular relationships, in fact, always exist. So let's go ahead and state the theorem, which is theorem 7.7. This is a theorem for 30, 60, 90 right triangles, theorem 7.7. and it states that the hypotenuse in a 30, 60, 90 triangle, I'm just going to abbreviate that, is equal to 2 times the short leg, as specified, abbreviating, and that the long leg, I'm going to abbreviate, the long leg is equal to the short leg x times the square root of 3, and so hence we have our theorem 7.7. Well, let's go ahead, let's do a problem regarding the relationships short leg versus long leg and the hypotenuse. Let me go ahead and scroll down. So let's assume I'm going to draw, see if I can't hand draw, at least a triangle here. This obviously is the long leg, so this is 60 degrees. This obviously here is the short leg, so this is 30 degrees, and here's my right angle. Let's get some values on this. Let's say, for example, we were given a hypotenuse. The hypotenuse was equal to 14, just a value of 14. Let me specify it here by the hypotenuse. We want to solve for both the short leg, long leg, excuse me, as well as the short leg. So let's start with the short leg. Short leg is much easier because we've got a value on the hypotenuse, and we know that the short leg is 1/2 of that of the hypotenuse. So let's specify that. The short leg is equal to 1/2 of the hypotenuse, which in this case happens to be 14 over 2, which gives us 7. Let's scroll up a little more, and let's take the long leg. The long leg, therefore, is equal to, recall that in the theorem 7, that it was the short leg x times the square root of 3, which in this case was x is equal to 7, from what we previously solved here, or the short leg. Therefore, 7 times the square root of 3, in fact, equals my long leg. And we have just used the relationships of the hypotenuse to the short leg and the short leg to the long leg. Thank you very much.